So I am recording this video at night instead of during the day, so I apologize for the stray reflections. I hope they aren't too distracting. Second thing, let's see what else. Oh, I just finished recording this once and it was like 12 minutes and I said, no, I am determined to get this shorter. So I'm going to try to give us a quick introduction to chapter 23. And when I say quick introduction, what I'm actually going to talk about right now is just the idea of conservative forces, the idea of a potential energy, the idea of a potential field. Okay, so let's go back to something you guys all know about, and we'll just talk about it really qualitatively. This is a difficult chapter to talk about because there's really one concept that we just kind of hammer in all sorts of different ways, and everything is pretty much contained in just one or two equations. So here we go. We've got some ball that's up here. If we let it go and we come down here, we know we are changing its potential energy. We know we have a higher potential energy here, a lower potential energy here. And once again, the only thing that matters is the difference in potential energy. We could measure this H from anywhere that we want to, but the thing that matters is the difference. So what does it mean? Well, let's just look at what's the work in this system. The work done in the system is just the force times the path. So what's the definition of a conservative force? The definition of a conservative force is if we go from point A to point B, and then we return to point A, so we do a closed loop integral of f dot dl, that this will equal 0. And what that means is essentially this. If we grab this ball and we pushed it right back up here, and we put exactly the same amount of energy into the system as came out of it on the way down the hill, then what we would get is it would sum to 0. We would get to exactly the same height. If we extracted a certain amount of energy, put that same amount of energy here, we go here. You can imagine that if this was a wooden block and this was a sand surface that was made of sandpaper, it wouldn't be true. We could put the exact same amount of energy into this system, but we would not get as high. And then this ball is going to come down, and the next time around we could put the exact same amount of energy from there, and it wouldn't get as high. And what that means is this would not be true. And that's called a dissipative force or dissipative force. It's called a dissipative force, and it is a non-conservative force. So what we are dealing with, however, is conservative forces where this is true. Well, what does that mean? It means a few different things. So the first thing it means is that we can express this force if we take this force and we say, what if it is the gradient of some scalar? And just as a reminder, you guys, this is du, the gradient is just du dx x hat plus du dy y hat plus du dz z hat. Okay, it's not critical that you know that. As a matter of fact, we're going to use shorthand right now, and we're going to call this, we're going to say that this is equal to du dl. Which is just another way of writing that same concept there. Okay, so the question is, what does f dot dl become if we do that? Oh, I'm sorry, there's something important to recognize here. This closed loop here, another way of writing this is we could say that the integral from a to b of f dot dl plus the integral from b to a of f dot dl, we could say that equals 0, right? In other words, we have just as much here as we have here. Well, what does that mean? If we look at this one right here, what it means is if we are going from A to B, we will gain just as much energy if we go straight down the hill as we will if we go around in spirals. There'll be just as much energy difference between these 2 points. Okay, and that's what another way of thinking about the conservative force, what a conservative force means. Well, if indeed, like we did in class, if indeed the force, it can be expressed like this, put another way, if it's a conservative force, it can be expressed like this, and the reason we know this is because if we do F dot dl from A to B, we end up with this U B minus UA. And it's actually, I apologize, there should be a minus sign here. There's a minus sign, and there's a minus sign. Is that right? I think that's right. Okay. So the point being that if we go from a region of high potential energy to a region of low potential energy, we are extracting energy from the system. If we are going from a region of low potential energy to a region of high potential energy, we are putting energy into the system. Just think about this ball on the hill. If we're here and we go from a region of high potential energy to low, then we are extracting energy from the system. But if we're going to put this ball back up here, what do we need to do? We need to put energy in to get it back up in that direction. Okay, so that's the first half of what you need to know for chapter 23. The second half of what you need to know we're going to cover in the next video, because what we're about to do is stop talking about gravitational potential and talk about electrical potential, or electric potential, sorry.